Good day, friends. Today we will be talking about an interesting story. This will be a linear story as we will be talking about the story of a line. We will not talk about its physical birth but the mathematical birth and its evolution also. As part of this story, we will encounter various terminologies which we are already familiar with, but we will be seeing it in a different perspective because it will capture the history of its evolution and the various neighborhoods that the lion will visit as part of this evolution. We will start with another inside story as part of this. Once there was a tall lamppost in a subway, and a task was posed by a mischievous person who told, find the height of the lamppost. And two friends were up to the task, an engineer and a mathematician. So to the engineer, all he gave was a very small ruler and said that you have to measure the height. Without the engineering tools at his disposal, the engineer was stumped. He thought for some time and he was about to give up. When the mathematician interfered, he, with all his might, he just pushed the lamppost down. Now, whatever it was in the vertical condition went to the horizontal condition, and it was a painful task, but the mathematician with the ruler, he could do the measurement. Now, what was the way the mathematician solved the problem? The problem was still existing, he solved the problem, but all he changed was the perspective, how he looked at the problem. That is the only thing. The story is not over. The engineer objected. He said the task was to find the height, not the length or the width. So, what is the contradiction here? We know that the problem is solved, but the terminology is the contradiction. Height, width, length are all merely terminologies. So, only the perspective matters and not the terminologies. Of course, the terminologies gives some history, which once again we will go through it. Now, in this story, the engineer and mathematician are not separate human beings. Actually, they are just part of the individual within us, because we are all made up of all these individual people. It is up to us to invoke the right person at the right time. That story, as it continues. So, at the end of the day, as those two people retire to their room, which they share as it goes, as the story goes, they have a very dilapidated room. So, there was often some sources of fire which used to happen, and they share the burden of putting it out. So, first, as they were both sleeping, at the first instance of fire, the engineer took the task. He went there. He, as always, ready-made fire extinguisher. He just switched off the fire and went back to sleep. Next, the turn was mathematicians. When the next incident happened, he went there. He saw the fire. He saw the fire extinguisher. He just made a statement saying solution exists. He came back to sleep. Now, you can guess what would have happened subsequently. So, that is what we mentioned. It is up to us to invoke the right person at the right time to solve the problem. Now, we know that the solution was existing, but he has not solved the actual requirement, which the engineer did. So in this case, the engineer actually solved the problem while the mathematician showed only the solution exists. So, once again, as mentioned, it's within us, we have to invoke the right person at the right time to get the right results. We will keep moving. Of course, we will keep tracking of both the perspectives of mathematician and terminologies of engineer as we move along. So, now what you see here is a German mathematician, Leopold Kronecker. He lived in around 1800s. He made a statement once that God created the natural numbers, all the rest were creation of men. Of course, there are various interpretations that he told a different statement. We will not go into it. But why did he make the statement? That can be the premise for our story. So, let's see the terminology natural in his sentence what he made. What's so natural in natural numbers? Of course, it's easy to see that natural numbers means 1, 2, 3 and 4 and so on and so forth. It is so intuitive that it is present even in any living beings. Take animal kingdom also. They can count their younger ones. They have the feeling of that and it's well established. Another instance is, it seems wolves, when they see a bigger animal, they increase the pack size, and when they see a smaller animal, they reduce the pack size. That way, they have an approximate kind of count. So, count is so intuitive that is present naturally, and hence the name natural. So, this is a terminology arrival, why it is called a natural number. Of course, it is physical also. What do we mean by physical? we can see a physical object and relate it to another physical object. Example is when we do counting by fingers, what we do is we show object and we start counting like 1, 2, 3, which maps this physical whatever shape in hand to some physical object that we have around us. That is the physical mapping that we establish as part of this natural number behavior. Now, having natural numbers either God given or intuitively arrived by nature, it's up to us to transact with it to move further. What do we mean by transaction? It's a give and take. And give and take is another way of talking about addition and subtraction. What happens as you play with natural numbers in this area? So, as you start adding two natural numbers, how does it behave? It's very easy to, you can try it. 2 plus 2 gives 4, 2 plus 5 gives 7. So, as you take two natural numbers and you perform the operation of addition, it gives always another natural number only. This looks slightly trivial because of course it should, but we will see the counterintuition in the next step. This can be seen as how it evolved, the grouping of animals or grouping of people. That is how this addition start coming into the picture. Now, what if we perform the other operation of removal, which is subtraction? Well, whether if we take two natural numbers and subtract one from the other, can we guarantee it will be a natural number? Why not we try it? Say 5 minus 2, straightforward, it is 3, a natural number. But what if we do 2 minus 5? We are stumped. Though we may have the education that says we can go into negative, but that's not natural. Can you show physically any negative numbers or negative objects? Now, the imagination starts cropping into our area. So, we go into a domain of imagination from physical. So, it's no longer natural, but instead of calling it unnatural, we call it as negative. This is exactly the birth of symmetry. So, one half you have already established a positive region where you started counting. Now, you have created by imagination another region which is a parallel universe. This parallel universe is actually the negative universe of it, which establishes the birth of symmetry. Now, this, though it may not be a very intuitive one, it still helps us to solve the problem of segregation. And this also can be the starting point of banking, because the credit debit is merely a operation that has cropped out of this addition and subtraction. So, from taking natural numbers by performing an operation of subtraction, we have created a new direction and it has given birth to a concept of symmetry. Now, let us play with those natural numbers. What if we keep a repeated addition, which is nothing but multiplication? Multiplication example is 2 into 3. 2 into 3, we know that we can always call it as 2 added to itself 3 times. So, we know that addition always gives a natural number, repeat addition is once again going to give a natural number, and hence if any multiplication is done on two natural numbers, it's once again going to give another natural number only. So, multiplication of two natural numbers, another natural number. But how about repeated subtraction? Repeated subtraction, as we know, we have a terminology called division. What happens when we do repeatedly subtract one natural number from the other? When we did the initial subtraction, we found a new direction called negative. Now, when we do a repeated subtraction, what it is going to give? Let's try it. 6 divided by 2 is 3. It's a natural number. You can even physically check it as grouping of sheeps. I have 6 sheeps and I am just going to pair it 2 pairs. So, I end up with 3 pairs. All are nice natural numbers which you can count. What if I have 5 sheeps and I now try to pair it? So, I will end up with 1 which cannot be paired. How do I represent it? I can always say 2 pairs plus 1 half pair. What do we mean by half? It is 1 of available 2. So, which we usually represent as 1 by 2, which gave birth to the world of fractions. So, from repeated subtraction, we get a new world of terminology called fractions, How do we represent in graphically? Like natural numbers initially was taking few points in the positive direction. The negative numbers gave the symmetry. Between those natural numbers, these fractions starts going and sitting. It starts filling the gap. Whatever gaps were there, now these fractions go and sit in that. Example, between 0 and 1, there is a gap, half, 1/3, 1/4, all these guys go and sit in those gaps and start filling that. But will they fill the entire gap? No, that's not always possible. Now let us see how further we can try to fill the gap, which once again we will slightly digress and say, we all know the elderly gentleman Pythagoras. He gave us the beautiful right triangle law in which the sum of squares of side length is equal to square of the diagonal length. So what you see in the triangle, the A and B being the side length, the squares of it summed up will becomes the square of the diagonal length. What's interesting here is, we have many solutions. For example, A is equal to 3, B is equal to 4. C, we get the nice solution as A square plus B square C square, and C will be 5. In that place, what if we give 1 for A, 1 for B? We end up with an interesting requirement of finding the root of 2. For Pythagoras, everything was a nice world. He writes in his front of school, the entire world is made of numbers. He likes only the whole number. He thought any number can be represented as ratio of whole numbers or ratio of integers. When he found a square root of 2 as part of his invention, and he found that he could not represent it as a fraction, whatever he tried, he was quite frustrated, extremely frustrated in that sense. To that extent, though he is being a rational person, he found that it's very irrational. To the extent he called it even illogical. So, irrational, this is how the terminology came into being, because he thought there cannot be any number which cannot be represented as a fraction or a ratio between two integers. That way, the terminology of irrationality came into the picture. But we all know that's a truth, it exists, root 2 exists, and so are other square roots also. Later, it was found not only the square root of 2, square root of any prime is irrational. What does it mean? Those numbers cannot be represented as ratio of nice whole numbers or nice integers or nice natural numbers. And hence, the root operation gave us a irrationality, which started filling the gaps between the fractions also, what we saw previously. Now, few more trigonometric operations yielded things like pi, e, and so on, which are not roots of polynomial, but still were irrational. And hence, the birth of transcendental numbers was put into that perspective. Now, all these, when you combine, they fill the gap. This is the point where we had been looking for. Now, we are ready to give birth to the line. So, we started with a natural number which had gaps. We used the negative numbers to create symmetry. We had rational numbers, which is nothing but fractions, which fill the gaps between the natural numbers. Then irrational numbers, which further fill the gap between the fractions, and transcendental numbers, filling some of the left out regions also. Now all the gaps are filled. Now we can walk along without worrying about falling anywhere in the real line. That is nothing but summation of natural plus fractional plus irrational distance. You can reach any point in a line that you had been looking for. This is the birth of a real line and birth of a geometry also, because now you can measure without worrying about any discontinuities. This also brought in the terminology of continuum. Continuum is nothing but between 2 points you can go without any issue in worrying about falling in a road. If you don't have any in between gaps, then you say that a road is a continuum. In this case, this line is a continuum. That being the story of real line, which we initially promised to tell each other and travel along. Are we going to stop at this? Yes, but not before exploring some of the neighborhood, which also we promised to explore. And before moving for it, why the name real came? Because we are exploring the terminologies also. It seems Descartes, another mathematician, when he was exploring the roots of polynomials, he came across the roots in positive or negative sense, and the roots which had negative numbers within it. So between these two, he wanted to differentiate. He named the positive roots as real, and the other one he left it to imagination, which became the imaginary number subsequently. Of course, the real statement itself, as we all now know, it's not true, because the real contains a negative number, and negative number cannot be physically shown. But of course, the name stuck. The real number now stands for the real line. And now let us move to the imaginary axis. As root of a number of or a prime gave irrationals, naturally the question arose, what will be the root of a negative number? The root of a negative number is the imaginary number that we all always have fascination to work with. Let us explore how the imaginary number can be represented. Real number, now we saw a nice graph as a line. Where does the imaginary number fit in? As you all know, I cannot put the root of a negative number anywhere along. Now the gap is filled, the road is filled. I cannot put in that road a root of an imaginary number. Where do I put it? Just extend my imagination. That leads to a very imaginary direction to explore. Real, already we explored. We drew a nice line. To bring in the negative numbers, we added a symmetry. Now we had a complete line. Where do we place this root of a negative number? There, rotation gave a beautiful direction. Let's try it before we make a statement. Let's convince ourselves by a simple experimentation. I have created a point in a real line. Let it be any point. It can be irrational, irrational, whatever we have now talked about. That point, when I multiply by a root of -1, where does this point go? It goes out of the real line. Let me place it in the other dimension. I create another axis which is rotated from here, and there I am going to place. Let me convince you by further experimentation. What if I multiply this by once again a root of -1? So we have two root of -1s now. So as it becomes, the root goes out and only -1 remains, which is a negative real number. So it goes here. Let us keep multiplying with the root of -1. It goes to the negative of I axis, and the last it reaches back to the starting point, which is the real number we started working with. So all you saw was, as we kept multiplying the imaginary number, all it caused was rotation of this point out of the real line, then back to the real line. So we have created what is the next dimension. So this is the beauty. Now initially with real we had one dimension. By bringing in the concept of rotation and the concept of imaginary number, we created another axis. This is one of the foundation stone for building of the higher dimensions. This is also the birth of it. So walking along real line and walking along imaginary line, we can travel anywhere in any of the operations till now we had been talking about. That usually is called the complex plane, because it is made of a real point and an imaginary point, which is usually represented by x plus iy. Now, have we covered all possible operations? Of course, our higher education usually stops here, but of course, our imagination doesn't stop. For the fun of exploration, there was one mathematician called Hamilton who kept thinking, should we stop this 2 dimension? Why not we keep extending it? So he tried to extend to n dimension and came with a beautiful higher dimension analogs called 4D quaternions. Do we stop? No, we can keep moving on and on. Of course, with its motivation application in computer graphics, robotics and orbital mechanics, we need to keep exploring, not just in complex number space, in hyper complex number space also. Whatever we started for necessity have become a mathematician's route for pleasure also. So what you see in this figure, the up to the third circle or ellipse, what you see Q is the quaternion, but then I am seeing more alphabets which is for higher dimensions also. This should also give you the thought that there are more spaces for you all and we all to explore. There is no limit. Earth's resources may be limited, but the mathematical resources are infinite for us to continue exploring. And as Kronecker said, now we can all accept God might have given us natural numbers and rest are all made by man. So when we quickly recap, with subtraction, we we got negative numbers and hence symmetry. With division, fractions were created, the rationals were born, numbers that can be represented as ratio of natural numbers. With root, we got the irrationals that filled in the gap between the fractional numbers, and combining the rationals and irrationals, we got the real number, which is the line which is also the continuum. With further imagination, the root of a negative number, we went to imaginary numbers. Beautifully, we have built a higher dimensional space from the natural numbers, which had been initially assumed to be given by him or nature or whatever it is. Now, having evolved a line and a plane, can we start decomposing it? Yes, if you can, something can evolve, it can also decompose because it's only the inverse operation. Let's decompose our favorite guy, natural number. What decomposition means? It is breaking into the fundamental parts, because the fundamental building blocks only makes anything. Let us see how we can break a natural number into constituent parts. Say 10, if I take, it is 5 into 2. The 190, 2 into 5 into 19, 360, 2 square, 3 square into 5. There is one something commonality across all this. You can see that those factors are all primes. So, prime number are the basis of any natural number. All decomposition leads to primes. So, primes can be considered as the base for the natural number. So, maybe Chronicles should have told God gave prime numbers, rest were created by the men and the people. So, this is can be called as a birth of building block or basis of numbers. Of course, this also can be representative for the birth of higher dimensional object. Each prime can be thought of a direction. So, we have already an infinite directional space ready for us waiting to explore. The natural world also we keep exploring, like atoms, quarks and subatomics. These are all the decomposition of the natural object as we keep trying to find what is the fundamental building block. We will try to explore some of the real life things that we come across in daily life, how we can decompose and understand it better. For example, language. How can we decompose a language? Take a simple word, asymptote. It can be split into a plus sim plus 15. What does it mean? 15 means being together, two things together in Greek. Sim means to fall. So, sim 15 is falling together, which doesn't fall together. As you know, asymptote never touches the line. It tries to touch, but it never touches. So, asymptote is a nice composite number which goes into the language roots. Maybe Greek and Latin, each of our language have its own roots which builds the entire language. That is language decomposition. Now, let us go to food decomposition. We have a variety of food items that we eat every day, as you see here. But this decomposition, we are not talking about the microbial decomposition, we are talking about the macro one. That has been, we can build all these food items with the raw material that we have here, of course, with varying quantities. That is a matrix that builds or takes in the food basis and leads to our whatever food space that we have to work on. Of course, color decomposition, we all know RGB is the fundamental part which builds the color space. After color decomposition that we just saw, when we go to decomposing sound, what we hear in daily life, it is made up of multiple frequencies. That is how we recognize people around us. We are able to create a signature of each people. Each have our own way of creating a pattern. How do we understand the pattern? It has lot of fundamental frequencies. Frequencies, when you talk about the vibrational system around us, on combination we recognize as a single pattern. Now, when we go to the fundamental frequency of it, we can see some interesting outcomes. Let us create some fundamental frequencies with our daily life pen. Here I will show you a simple demonstration of it also. What I am having in hand is a pen cap. And what you see in the screen is a spectrum analyzer. Spectrum analyzer merely converts the sound into frequencies. The x-axis is the frequency and y-axis is the amplitude. Now you are able to see two peaks. First is the fundamental peak and second is its overtones of it. Going back to our presentation. So this is whatever animation you see is nothing but the pen, and you can see the air molecules actually vibrating in it. And the first mode is shown. Second mode is nothing but the second frequency component that you saw subsequently in the frequency spectrum. Now what if I want to create more such frequencies? All I have to do is have more higher length pen caps with me. That is nothing but the pan flute, which is a Native American flute. But how do Indians work with it, or some of our other religions? Instead of changing the length of the flute, what we do is we create a single length flute with multiple holes in it. This also I will just demonstrate to show how the frequency component varies as we change the length of it. Let me start with the fundamental frequency. You could have watched the peak nicely moving. It is nothing but it shows that the frequency content, as you keep changing the whole position, it was traversing one octave. Octave is a frequency to 2 of it, twice number of it. This is how we can decompose a sound by you can recompose a sound by combining all these frequencies. This is the sound spectrum basis. So what we have seen is basis or the building block of all these natural systems. Now the question again, on the screen you see a tree and a nervous system of a human. Can we think about a basis for such things? Till now we were able to, for numbers we had prime as the basis. For sound, color and also for other physical things we had some hint of even food we had a basis. For these kind of seemingly complex things, can we think about a basis? Can we decompose them? There is one hint that we see here. It looks there is some similarity, there is some self-similarity. How do we see that self-similarity in work? I will show you by a simple demonstration again. So on the screen what you see is a combination of few lines. Now let me take one of each of the line and replace by the mother combination of lines, which means I am making each line to be self-similar to its parent. First iteration let me run. Let me go for one more iteration, all the lines replaced by mother line. Already you can see a pattern evolving. It's slightly computationally intensive. Now you can see the bush ready for you to handle. And all you had initially was this fundamental line. So this is the natural basis. We can play with the natural basis and create any natural elements that we want. So I just wanted to show you that how from simple lines we can create seemingly complex things by self-similarity activity. Now there is one secret that is held here. What is the dimension of it? We saw one-dimensional real line. When we created another imaginary line, it formed a plane. Now where does these fit in? These, whatever or how many ever times you repeat, it never will fill the space. So it is a fractional dimension, and hence it has a beautiful terminology called fractals. It fills a fractional dimension, and hence we get the birth of fractals. So from natural number, we walked along with our imagination, we created higher dimensions and even fractional dimensions. With this, I just thank our chroniqueur for giving the premise for the story to create the line and to create its neighborhood, and thanks to all of you for walking along with different perspective and exploring the story of line and its neighborhood. Thank you.